Greetings, welcome back. This is Introduction to Linear Regression. We're doing Fitting Least Squares Regression Line Part 2. In this part, we're going to go ahead and actually take some summary data, and we're going to take that summary data and create the regression model based upon the formulas and stuff we talked about in Part 1. So this is based on 7.25, which is why we reviewed 7.13. We needed to know what we were talking about there. Okay, so they want us to write the equation of the regression line for predicting the travel time. So what we're going to need to know is we're going to need to know what is the mean of the x's, what is the standard deviation of the x's, what is the mean of the y's, and what is the standard deviation of the y's. And we're also going to need to know what the correlation coefficient is. So we have all that information given to us in the opening paragraph here. The mean travel time from one stop to the next is 129 minutes with a standard deviation of 113 minutes. The mean distance traveled from one stop to the next is 108 miles with a standard deviation of 99 miles. The correlation coefficient between the travel time is 0.636. So let's go ahead and do R right away. So that's 0.636. And now let's talk a little bit about who's the X and who's the Y here, okay? Well, we're supposed to make the predicting the traveling time, okay? So if we're saying we're predicting the travel time, then that means the travel time is going to be our response variable. And since that's our response variable, then that means that that refers to us that that's our Y variable. So travel time is the Y. So let's come back up here and take a look. Well, that means that we have travel time from one stop to the next is 129 minutes. So that's 129 for Y bar. And the standard deviation was 113 minutes. And then for X bar, the mean for the distance traveled, in other words, we're saying the distance traveled is predicting the time. That's 108 miles with a standard deviation of 99 miles. Okay, so now notice that both of these are in units of miles. Both of these are in units of minutes. And this is unitless. That's all going to be important. We're going to want to remember that, okay? All right, so we need to go write down the equation of the regression line. So to do that, what we're going to do is go ahead and get ourselves a blank sheet here, okay? And remember that first off that B1, which is our slope, is equal to the standard deviation of the y's divided by the standard deviation of the x's times the correlation coefficient r. So in our case, what that means is that the standard deviation of the y's, if you remember correctly, was 113. Standard deviation of the x's, that was 99. And we're going to multiply that times our correlation coefficient, which is 0.636. All right, so let's go ahead and go back over to RStudio. We'll put that in an R chunk and let R do that calculation for us. So, because we're going to need that number, so we'll come down here and say, okay, so let's take 113 and let's divide that by 99, and then let's multiply that times 0.636. Now, of course, you're perfectly welcome if you feel more comfortable. Just go ahead and do it on your calculator, but I'm going to do it here. And so that tells me that first off, if we come down here, we'll just type in, looks like the slope, the estimated slope, is going to be equal to what? Well, let's go out 3 places. So the slope will be equal to 0.726, excuse me. So 0.726 is what our slope looks like. All right, so to get the actual equation of the line, let's go ahead and go back over here to the whiteboard. To get the equation of the line, we're going to use those formulas, second part of those formulas that we talked about a minute ago. And what that says is that we know that y hat minus y bar is going to be equal to b sub 1, which is our slope, times x minus x sub bar. Okay, again, this is just our old pal to point slope formula. So what we need to do now is come in and plug in the numbers for the mean of the y's, the slope, and for the mean of the x's. So let's go ahead and do that. So let's see here. What was the mean of the y's? The mean of the y's, I believe, was 129. You know, it's probably not a bad idea. Let's just take a second here. Let's go move our numbers over from the previous page. So we knew we need the 108 and the 99 for the x's. So let's bring those back over here. So our x bar is equal to, I can't even carry it for more than 30 seconds, my poor old brain. Let's see, 108 and 99. There we go. So that's 108, and the s sub x is equal to 99. And we calculated the b1 down here to be 0.726, if I recall correctly. Let's see, actually we have that over in RStudio. Let's go get that from there. So we got that out of the calculation there. So we got it, yeah, 7.26. So bring that back over. It's good just to get all those things in front of us in one place so we don't make a mistake typing the numbers in the wrong way. Okay, so that is that, and then we've got that the y hat. Let's go take a look and see what our y hat's going to be here. Let's get the right slide here, Mike. You can do this. I know you can. We got 129 and 113. Okay, cool. All right, so let's go plug those numbers in. So the y bar is 129, and that's equal to our b1, which was 0.726, times our x minus our x bar, which is 108. Okay, so what we're going to do now is we're going to get this set up into y equals mx plus b format. In other words, we're going to solve this for y hat, so that's going to be y hat is equal to 0.726x minus 0.726 times 108 plus 129, okay? All right, so now what you need to do is do a little bit of arithmetic. So I just took a quick little pause there to go do the calculations. Okay, so this comes back to be 0.726x, and then plus, well, I'm going to go ahead and leave it out to 3 places, so we'll go out to 50.592. But there is an argument based on sig figs of rounding that up to 51, but since we went out to 3 places on our slope, I think we'll go ahead and go out 3 places there. Okay, so let's go back and type that in, because we need to have that in our solution here. What we were looking for in this particular problem down here was actually what was the regression equation. So we're going to go ahead and do a little bit of tech here, because remember you can use tech to help you get your mathematics looking really nice. So it's going to be what? Let's see, that's going to be, it's / hat is how you do it. And then you put in a y is equal to 0.726 x, and then we're going to put in a plus 50.592, if I recall correctly. Let me just check, make sure I got that number still in my head. Yeah, 50.592. Okay, great. And then close off with the closing dollar sign. And when we go ahead and knit that, that's going to come out nice and pretty. Okay, interpret the slope and the intercept in context. Okay, so remember we talked about that there were units involved in the slope. So let's go back for a moment to our whiteboard and take a look at that. And we said we know what the units were involved here. We know that this numerator was in minutes and this denominator was in miles. Because remember, the s sub x's are in miles and the s sub y's are in minutes. So that means that the slope right here has units involved in it. It's in minutes per mile. And what that tells us, if we come back over here and type that up nice and neat, it's all sloppy here on the whiteboard, is it tells us that it takes about what? 0.76, so for every 0.726 miles we travel for 1 minute. Okay, so the slope has units in minutes per mile, excuse me. I'm so conditioned to say miles per minute, but it's not. It's minutes per mile. And what that means is that it takes that many minutes for every mile that you pass to get from one station to the next, okay? So it takes about, if I could type, that would be such a wonderful thing. About 0.726 minutes for each mile. Okay, now what does the y-intercept mean here? Well, the y-intercept means that if you're going 0 miles, right? In other words, if you put in x as your miles, it's going to take you 50 minutes to go 0 miles. That doesn't make any sense. The intercept is at what? It's the ordered pair 0 by 50.592, right? And what that particular intercept really doesn't make any sense in context of the problem, okay? It's simply there to adjust the line so that we get it in the right direction, okay? So keep that in mind. Sometimes the y-intercept will have a meaning if 0 is in the data set, or if it makes sense to have 0 in the data set, but many times the y-intercept will not have any sort of meaning in it. Okay, so now they want us to calculate r squared, which is the regression of the regression line for the predicting travel time from distance traveled for the coast starlight, and then interpret what does r squared mean in the context of this application. Okay, so let's go ahead and use RStudio again just to do the grunt here for us. Again, of course, you could use this on your calculator if you want to, and we would see that it's what, 0.636 squared, and if I go ahead and execute that chunk, it gives me back 40.4496. Okay, so let's go ahead and come down here and say, go ahead and we'll do a little treachery here, and we'll do this in as a LaTeX thing, and we'll say r squared is equal to 0.40, or, oops, my bad, I'm going to close the dollar sign there, or 40%, okay? So what does that mean in context of the problem here? So what does the correlation coefficient mean, and then what is r squared, which is not the correlation coefficient, by the way. R squared is called the coefficient of determination, and that means that what? About approximately 40% of the variability in travel time can be explained or is accounted for, but let's say it can be explained by the model. In other words, by a regression line, okay? And then so there's more variability than can be explained by just the model, all right? In other words, there are other factors involved here besides just our regression model. All right, so the distance between Santa Barbara and Los Angeles is 103 miles. Using the model to estimate the time it takes for the starlight to travel between these two cities. Okay, so back up here we've got our regression line, and so all we've got to do is plug in that value in for x, in other words that distance, the 103 miles, to get back what the time is going to be. So we put in our slope, which is 0.726 times, let's go ahead and just put an asterisk in there, 103, and then we're going to add to that the 50.529. Okay, all right, we'll go ahead and execute that, and it takes about 125 minutes roughly, or you could say about 126 minutes, right? So I would say about 126 minutes. We're going to go ahead and round up. And the reason we'd round up here is that, you know, you don't want to tell them you're going to get in there in 125 minutes and then not, right? You could say if you said 125, it's no big deal. Okay, so it takes 168 minutes to travel from Santa Barbara to Los Angeles. So calculate the residual and explain the meaning of the residual in this value here, okay? Well, remember that to calculate a residual, we take the observed minus the expected. So the observed in this case was 168. So we take 168 and we subtract from that our expected, which is 126. And that gives us back a residual of 42. So the residual is 42. And so what does that mean? Well, we have a positive residual. And since we have a positive residual, so we overestimated, right? Or do we over or under? No, we underestimated, didn't we, right? You can tell that just actually by looking at the numbers that we underestimated it. Okay. Suppose Amtrak is considering adding a stop to the Coast Starlight 500 miles. Get back here and put a period in there, a couple spaces. There we go. 500 miles away from Los Angeles. Would it be appropriate to use this linear model to predict the travel time from Los Angeles to this point? Well, let's go back and take a look at our opening graph here, so to speak. Okay, our opening scatter plot. So if we go back and take a look at the scatter plot, what we see here is that the distance in miles was, I don't know, say 20 out to the largest distance that we had. Remember, these are units of 100, okay? So that right there, at best case right there is like at 350, isn't it, right? So the thing to keep in mind is that it's a really bad idea to extrapolate. We don't know if the trend is going to continue. So even if that was 350, 500 is going to be like way over there someplace. So it's going to be outside of the regime of our model, outside the domain of our model. So that would be a really bad idea because we'd be extrapolating, okay? And so the answer to the question is no, that would be extrapolating, which is bad juju. Okay, all right, maybe get a little more serious about it here, is a bad idea. Because we don't know if the linear trend continues, all right? All right, so that was quite a bit of work, but not horrible. Notice that you can do most of all these things by hand, really without using much of RStudio. You could do all those calculations using your old probably do it on your phone for that matter. You just use your regular old calculator. Okay, so we're going to come back after this one and do part 3, and what we're going to do is take a look at how to do a regression line with data, which is a much more practical real-world example.